Hello students, welcome back again for the another session of the econometric methods course. Today we are going to see the different tests that are available to assess or confirm the presence of heteroscedasticity problem. After that we are going to discuss about the remedies for the problem. All the tests are based on the estimation of error values. In fact, the proxy for variance is taken as the modulus of the error term or E square. Therefore, in all these tests, the first essential stage is to estimate the error value. First, I am going to teach you how the error values are estimated. Then we will see the different tests. The tests of heteroscedasticity problem starts with the estimation of the proxies for the variation of the error terms. The variations of the error terms are identified with the absolute value of the error term or the square of the error term. First, we will see how these proxies are estimated, because most of the tests are based on these proxies. Now, let us see one example of that. Consider a saving function. Actually, it is already estimated. Y hat is equal to minus 0.2 plus 0.46 x. So, it has got the data. This is the x data and this is the y data, and we may find the y hat using these the function. For each value of x, we can estimate the estimated value of y. So, we just got this 4.4 corresponding to these two values by this equation, minus 0.2 plus 0.46 into 10x. We are substituting the x value, and this would give you the 4.4 value. Similarly, the 6.7 is found minus 0.2 plus 0.46 into 15 would give this value, and substituting this 20 in this equation will get 9. Substituting 25 in this equation will get 11.3, and 30 is obtained by substituting the value 30 instead of x. So, after identifying this, after calculating these values, we can estimate the error value. Error is nothing but y minus y hat. It is simple, we are subtracting these two columns. Subtracting these two columns, we will get these error values, y minus y hat. So, just 5 minus 4.4, 0.6, 7 minus 6.7, 0.3, 8 minus 9 minus 1, 10 minus 11.3 minus 1.3, 15 minus 13.6, 1.4 you will get. So, after this, the proxies for the variance, error variance is found for each observations. Either the absolute value of this is taken or the square of this is taken. The first column is the absolute values of these error terms, 0.6, 0.1, plus 1, plus 1.3, plus 1.4. The square of it is the second column. So, we get 0.6 whole square is equal to 0.36, 0.3, 0.09, 1 square 1, minus 1.3 square 1.69, the square of 1.4, 1.96. So, you get these columns. For each corresponding values of x, you get the error terms. So, with these values, we can do the tests. The first test is the very simplistic test, graphical test. we order the observations by x or y hat. If you are using the MLRM, y hat is better, otherwise in SLRMs x is taken. So, we order the observations either by x or y hat according to the model that we are using. Then after ordering the observations, the entire observations by x or y hat, we will get two values. We can draw a scatter plot for E square against x or y hat, So, we are running a scatter plot for this against either this value or this value. So, in this case I have shown the simple regression model, and so I am going to draw a scatter plot for E square against x. Any systematic pattern other than the band would indicate a presence of heteroscedasticity problem. Let us see the picture shown to you. The first scatter plot is like a band, right, without having any much variation across different points of x. So, it is uniformly distributed like a band. This indicates the homoscedasticity. The other pictures, all the rest five pictures are shown. All the other pictures have got one pattern or the other than the band that we saw in the first diagram. All indicate the heteroscedasticity problem. The graphical tests, though may look very simple and nicer, the statistical tests are very essential to confirm the presence of heteroscedasticity problem. In this case, the second test is rank correlation test. We are going to find the rank correlation between E, absolute value of E against x or y hat. So, we have to find the rank correlation between modulus E and x in this case, or modulus E and y hat in the MLRM case. So, the correlation coefficient usual formula, the rank correlation formula, R is equal to 1 minus 6 sigma d square divided by n into n square minus 1. D is the difference in the ranks, D is the difference in ranks of the two individual observations on modulus E and x. So, after finding this rank correlation, we can construct a test statistic like this, R by square root of 1 minus R square into square root of n minus 2. In this case, actually this is an SLRM, and this statistic follows the normal distribution with 0 mean and 1 variance for the large sample. For the small sample, if it is a multiple linear regression model MLRM, T follows T follows the T distribution with n minus k degrees of freedom. So, we have the calculated value based on this and the table value based on these distributions. So, you can find the calculated value and you can find the table value according to the level of significance and the degrees of freedom. We may confirm the presence of heteroscedasticity with a simple decision rule. If the calculated value is higher than the table value, we may confirm the presence of heteroscedasticity. Now, let us move on to the third test, Goldfeld quant test. In this test, the observations are ordered either by x or by y hat. So, n samples are first ordered by the magnitude of x or y hat. After that, we will remove the p middle observations, p number of middle observations. After removing, we have on both sides n minus p, because total sample size is n, and of which p is removed, p observations and the p data points are removed. Then we are left with n minus p observations. On the whole, it is equally distributed in the lower and upper end, and so you have n minus p by 2 samples in the lower end and n minus p by 2 samples in the upper end. For these two different sample points, you can calculate the error sum of squares, and you can find the error sum of squares for the second sample. Actually, this is the error sum of squares for the first sample and error sum of squares for the second sample. Based on this, you can define a F ratio. So, the ratio between the error sum of squares of the first sample divided by degrees of freedom and the error sum of squares of the second sample divided by degrees of freedom. Degrees of freedom here is nothing but n minus p minus 2k divided by 2, where k is the number of parameters to be estimated. In this SLRM, 2 parameters are estimated, and so k is equal to 2 here. So, based on this, this value can be calculated. This is the calculated value, and also we can theoretically prove that this ratio follows a F distribution with n minus p minus 2k by 2 comma n minus p minus 2k by 2 comma 2 degrees of freedom, F distribution with these 2 degrees of freedom. And from this, with appropriate level of significance, we can find the table value. You may compare this to come to a conclusion about the presence of heteroscedasticity. If the calculated value is higher than the table value, we may confirm the presence of heteroscedasticity problem. Now, we will see some tests based on the auxiliary regressions. Actually, these are all secondary regressions apart from the primary regressions that we do for the regression models. These are all secondary regression models. So, based on the error terms or the error variance proxies. So, Kledger suggests some 6 types of specifications for this test. The first one is EI, the modulus EI as a function of modulus EI based regressed on xi, modulus EI regressed on xi square, modulus EI regressed on 1 by xi, modulus EI regressed on 1 by square root of xi, modulus EI regressed on log xi, modulus EI regressed on square root of alpha, square root of a linear function of xi. Of this, the first 5 specifications can be run with OLS, and this can only be run with other than OLS techniques. So, here the test is very simple. The segment test for alpha 1 would be the test for homoscedasticity problem. So, here we can very easily test the significance of alpha 1. This is a simple regression model, and we can find the standard errors of alpha hat, alpha 0 and alpha 1 using the OLS procedure, and we can find the t values for this regression coefficients, and so we can find the significance of alpha 1, and if alpha 1 is significant, that will indicate the presence of heteroscedasticity problem. So, this is very simple procedure used by Kledger, and very similar one is the Park's test. Actually, Park test is based on instead of based on the absolute values of EI. Here the test is based on EI square and in the logarithmic form. The significance of alpha 1 would be the test for the homoscedasticity, and the significance of alpha 1 indicate the presence of the heteroscedasticity problem. So, if alpha 1 is significant, we will say there is a problem of heteroscedasticity. But the main issue in this whole thing is that sometimes we have to use the more sophisticated other than OLS regression estimation techniques, and the main issue here is most of the time we do not do tests of heteroscedasticity for the error term used in these auxiliary regressions. The next test is White's general heteroscedasticity test. This is a generalized test. This tests the specification problem and the heteroscedasticity problem, and so this is called generalized test. Let us take one a simple multiple linear regression model. Y I is equal to beta 0 plus beta 1 x 1 I plus beta 2 x 2 I plus u I. From this equation, after the estimating this regression, we can estimate the error square, EI square. Now run the EI square regression of EI square on x1I, x2I, x1I square, x2I square, x1I, x2I plus Vi. We may also include some powers, higher powers of x's according to the requirement. This regression will run it and will compute r square and n r square. The n times the r squared is the test statistic. This n into r square is found to follow the chi-square distribution with k minus 1 degrees of freedom, where k is the number of parameters estimated in the auxiliary regression. Here in this case, we are estimating 6 regression coefficients, and so k is equal to 6, then k minus 1 is 5. So, this regression we will use and we will compute r square and nr square, and this will give you the computed value, and chi-square distribution with k minus 1 degrees of freedom will give you the statistical value according to the we will get the level of significance, and based on the level of significance we can find the table value. So, you have the calculated value and the table value. Comparing it will give you the test result. If the calculated value is higher than the table value, then we may confirm the presence of heteroscedasticity problem. As I told you earlier, this is a generalized test. If you include this cross multiplication term, this alpha 6 would serve as the significant test for the specification test. If we do not include this term, this is a pure heteroscedasticity test. Now, let us see the last test, Bruce-Pagan-Godfrey test. This is a Lagrangian multiplier test as in the previous case. Here in this case, we are going to let us take one example. This is the original regression model. We will estimate the EI square, error sum of squares, and estimate the variance of it, UI, variance of UI, that is sigma hat square. So, with these two values, the estimate of EI square and the variance of sigma hat square, we may define one standardized error square measure, that is Pi. Pi is equal to EI square divided by sigma hat square. This is a standardized error square. We are running a regression of Pi on the regressands x1i and the independent variables x1i and x2i. So, this is an auxiliary equation. From this auxiliary equation, we may find the error sum of squares divided by 2, error sum of squares divided by 2, and this will serve as a test statistic. This ratio is found to follow theoretically the chi-square distribution with k minus 1 degrees of freedom, where k is the number of parameters estimated in the auxiliary equation. Here in this case, 3 parameters are estimated, and so the number of parameters here k is 3. So, k minus 1 is 2. So, for this equation, the error sum of squares divided by 2 follow chi-square distribution with 2 degrees of freedom. So, we can calculate the calculated value, we can compute the calculated value using this and the table value corresponding to the level of significance, and this chi-square table, we can find the table value. So, comparing these two, we can confirm the presence of heteroscedasticity problem if the calculated value is more than the table value. One good thing about this test is, actually this is a popular test. One good thing about this test is that no prior specification of heteroscedastic structure is required. Actually, this is a generalized test for all kinds of heteroscedastic structure. Now, let us see, after identifying the heteroscedasticity problem, how to remedy that. Once the presence of heteroscedasticity is confirmed, it has to be remedied. There are two broad categories of remedies in the literature. First, when the variance is known. When the variance is known, we have some set of procedure. When the variance is not known, there are other set of procedures. Let us assume sigma I square, sigma i's are known. Consider MLRM yi is equal to beta 0 plus beta 1 x1i plus beta 2 x2i plus ui. Divide both sides by sigma I, the known sigma I, we get yi by sigma I, that is equal to beta 0 sigma I plus beta 1 x1i sigma I, beta 2 x2i by sigma I plus ui by sigma I. The variance of this equation is constant. Actually, this is a very simple, it is easy to verify it. The variance of sigma ui by sigma I is constant, is actually in fact is 1. So, ui by sigma I is homoscedastic, and so this regression does not have the problem of heteroscedasticity. The application of OLS would yield blue estimates for this regression. So, this procedure is also known as generalized least squares method. So, this method, generalized least squares method, will get you the correct estimate, and that model can be interpreted as the regular model. There are other set of procedures, that is the second set of procedures. Here we call it sigma I square is not known. Here we presume, instead of knowing the values a priori, here we assume the variance is in proportion to the square of the estimated y, or the variance is proportion to the directly proportional to the estimated values of yi straight. In both the cases, just a transformation. The GLS is applied with different transformations. First, assume the variance is in proportion to the square of the estimated yi. In such case, if you divide the entire equation by yi hat, after this division we can run the ordinary least squares. The error term will say will clearly indicate the variance of the error term is constant here, and so homoscedastic error term this equation has if the heteroscedastic structure is like this. So, after this transformation we may run the OLS. This procedure is called GLS procedure. This GLS procedure will get you the blue estimates. And similarly, in the second assumption, if the variance is proportional to the estimated value of yi, then we may divide the equations by square root of yi hat. So, if with this heteroscedastic structure, the error of this equation ui by square root of yi hat will yield the heteroscedastic homoscedastic error homoscedastic error, and so this transformation will get us the blue estimates. So, these two are no trial and error methods. We can test and know afterwards if there are still the heteroscedastic problem exists in this error, then we have to go for we have to look for other methods. So, the other method is taking log. So, instead of running the regression of the variables in its levels, we may run the regression on the logged values of those variables. So, log yi is equal to beta 0 plus beta 1 log x 1 I plus beta 2 log x 2 I plus ui. This equation will solve the problem of heteroscedasticity. The last method, the last procedure we can think of as White's heteroscedastic consistent standard error procedure. White suggested the procedure to compute the heteroscedasticity consistent standard error. Consider a regression model yi is equal to alpha plus beta xi plus ui. Here the variance ui is equal to sigma I square. Traditionally, in the presence of heteroscedasticity problem, the variance of beta is computed as sigma xi square sigma I square divided by sigma xi square the whole square. We may replace the sigma I square with the estimated error square. So, ei square may be replaced may be used to replace the sigma I square, and so the variance of beta hat now is sigma xi square ei square divided by sigma xi square the whole square. This variance is considered as a heteroscedastic corrected variance. Instead of the old variance, this corrected variance is used to compute the standard error and to compute the t ratios. So, this t ratios will not mislead. This will tend to the corrected t values if the sample is quite large. So, this t ratios will give the realistic statistical inference for the regression coefficients according to this procedure. To explain the remedies, we can compare the standard errors of the different methods in the presence of heteroscedasticity problem. To give the explanation, I am taking the example from the basic econometrics book of Gujarati, the 4th edition. In that, the relationship between the research and development expenditure and sales of 18 industries in US in 1988 is given. The first model, the ordinary least squares model, and this model gives actually the results like this, and it was confirmed in the example that the model has got the heteroscedasticity problem. And after identifying the heteroscedasticity problem, it is found that the variance is in proportion to the sales revenue, and so the transformation is suggested. We just divided the entire equation by the square root of sales, and that model has yielded the GLS results, the generalized least squares results. And the third one is the third equation. Actually, the usual regression is run, but with the corrected standard error is computed for this model. You may compare the standard error. Actually, the values given in the arc bracket is the standard error of the respective regression coefficients, and the square bracket gives the t ratio values. So, the respective t ratios are given in the square bracket. You may compare the standard error computed on 3 procedures in the presence of heteroscedasticity problem, right. So, this is the heteroscedasticity computed, this is the standard error computed in the presence of heteroscedasticity in the OLS. This is the standard error of the GLS procedure, and this is the heteroscedasticity corrected standard error. Of the three, you may straight away compare. There was a great reduction of standard error. Actually, it was greatly higher, and this is about 14% of the standard error is reduced. So, this t values may give a very realistic statistical inference than the statistical inference based on this the OLS t values in the presence of heteroscedasticity problem. So, in the example we saw that the regression coefficients, especially the slope coefficient, the beta, does not vary much. At the same time, the standard error greatly varies for different models. So, we have known that the heteroscedasticity, the presence of heteroscedasticity affects the standard errors, but not the regression coefficient estimate itself. Okay, now we can conclude this module that we have seen so far the different tests used in identifying the presence of heteroscedasticity problem, and also we saw how this problem can be remedied. We saw the different methods of remedying this heteroscedasticity problem. With this session, we conclude the session on heteroscedasticity problem. We will see the other problem, namely the multicollinearity, in the next module. Thank you.